Rotational kinetic energy is it's the same formula as kinetic energy.
Rotational kinetic energy is nearly the same as kinetic energy. It's a good question. In fact, I think I can answer that. Let me just draw since you asked, I'll draw the parallels. So, E kinetic linear equals 1/2 mv squared. So we can just think of it this way. I mean, here's your mass, and there's your velocity, right? Another thing worth noting is that we know that velocity is a vector. There's another way to write it. It's 1/2 mv dot v, and so that's the dot product. And another way to write that is 1/2 mv times v. Actually, I won't use that one. I'll just say v squared cosine of theta. Now, where's theta? Theta is the angle between v and itself, and it's 0. So it's 1/2 mv squared times 1 equals 1/2 mv squared.
Right.
Okay. So because we know that velocity is a vector, but in this case it kind of doesn't matter. So there it is. The rotational E kinetic, because it's moving, rotational equals 1/2 I omega squared. Now, this velocity, we normally think, okay, it's going in a straight line. Nothing really goes in a straight line. Throw a baseball, it's moving in a parabola. The moon's moving in an ellipse. Show me something that's moving in a straight line and just back out a little further, and it's a curve of some type. But so the way to think about this again, if we just had some point, and then here's your mass, and it's traveling in a circle, instead of a line. It still has a velocity.
Right.
It's got a velocity there, it's got a velocity there, it's got a velocity there. It's just easier, rather than having all those velocities, to just give it a single omega. And incidentally, the relationship between v, and actually omega itself is a vector.
Right.
And it's pointing, so you're like, well, which way is it pointing? Well, if it's spinning, let me do my right hand, if it's spinning this way, it's pointing up. If it's spinning this way, it's pointing down. If it's spinning that way, it's pointing left, spinning that right, front, back. So even though when something's spinning, it's sort of going every direction at once, the direction of spin is whatever axis it's pointing about. And that's how we give that a vector. Okay. So you can also think of, sort of, and they're just for the sake of completeness here. Polar vector. Yeah. So there's two different ones, and it's worthwhile noting there's a polar vector versus an axial vector. And we'll just I love Wolfram. These guys are quite good. So, and I guess what they're doing with these planes is showing when you reflect them. When you reflect this black one across this line, they're going in opposite directions, like looking in a mirror. But in this case, when you reflect the black axial vector, they're not. They're still spinning in the same direction, yeah. So anyway, that's the difference between the polar versus the axial vector. Okay. So yeah, kind of, I don't know how to explain it. It's still, they're both still energy. One's spinning and one's just moving in a so-called straight line. Okay, so how does this affect wind turbine design? Well, we've mentioned that if wind is blowing towards a turbine, so let's just let this be a turbine, the wind is going to have some velocity. It also might have some acceleration. If it didn't, the wind would be just blowing the same time all the time. But it's not. Like sometimes it's speeding up, sometimes it's slowing down. So the velocity and the acceleration of the wind in a linear fashion will affect the angular velocity and the angular acceleration of the turbine. Like the turbine's going to speed up and slow down as the wind speeds up and slows down. We already looked at the angular, or so the rotational energy, and you can do the same thing. You can go out and look up the. I still have this guy. So if we go up, these moments of inertia, this one in particular is the moment of inertia of a single wind turbine blade.
Okay.
So you go stick that turbine blade on a scale, measure how long it is, divide it by 3, and there it is. That's its moment of inertia. And then you add 2 more, and you end up with your ml squared, because you typically have 3 blades on a lot of the more popular designs. So there's that. I'm also making the point here that a wind turbine typically has fewer blades. A windmill is typically going to have more. The tip speed ratio might be 4.5. So the tips of these blades are going to be going faster than the wind, maybe 4.5 times faster, whereas the tip speed ratio in a windmill is going to be lower. This guy is higher speed, this guy is higher torque.
Right, 'cause it goes slow.
High speed, high torque, yeah. Might be the same power, just as powerful, but just think of your car accelerating in first gear trying to get up a hill with lots of torque, lower RPMs versus speeding along the highway, relatively little torque, but higher RPMs but a lot more drag. But could be the same exact power. Yeah. So there's tip speed ratio, jaw. So we can refer to the textbook here. Let's just look at jaw 336. Yeah. So here we are in the textbook. This is jaw 336, and there's lambda equals V tip divided by V naught. So that little symbol right there is a 0, and that's just the speed of the wind. So there you go. An intimate relationship exists among tip speed ratio, rotational speed, and rotor size. The tip speed ratio is defined as the ratio between the speed at the tip of the rotor blade and the undisturbed wind speed. Now, here's another thing to keep in mind, is that the velocity at the tip equals the radius of the blade times 2 pi times omega. So the bigger the blade is, the bigger the blade, and that's just making it around the around the loop once, and the faster it's spinning, the faster the velocity at the tip. So let's draw that. So just look head on into wind turbine. So here's your omega. V-tip, this is what we kind of been talking about. Obviously the blade does not go in that direction, but instantaneously it does. You know, it's about to head down here. So here's V-tip. V-tip equals 2 pi r omega. And here's r. Measure from the center of the blade out to the edge. So the bigger the turbine, the faster it goes, the faster the velocity. And then back here, this lambda is V-tip divided by V naught, so 2 pi r omega over V naught. Okay, so that's your tip speed ratio. Okay, a couple other things. I would like to hold you to this. I would like to have one or two little questions on this. So we've talked a little bit about vectors. Talked about the fact that velocity is a vector. We've also used to talk about the fact that a force is a vector. So if I'm pushing, let's just say on my hand right here, but the only two directions I have to work with are X and Y. In order to figure out how hard I'm pushing, I have to add up those two components. This is actually very important when putting any kind of wind or solar technology on your house, because you do not want the roof of your house to rip off. And the way to do that is to put screws, nails, etc., to keep it in one place. What I'm showing here is this force, and I just put it as F sub t. You could think of that as the total force, is a combination of lift, which is the force that's going to lift your roof off of your house, and the drag, the force that's going to push your house over. So total force equals the drag plus the lift, or the lift plus the drag. Now, we can go right back to Pythagorean theorem. If we want to know the magnitude of that total force, we just use Pythagoras. Square that, take the square root, and you're done. So there it is. Now, why is this important for wind? Well, you've got two types of turbines. You've got Savonius and Darius turbines. Savonius work on drag. It gets pushed along, and you've got Darius, which work on lift. It gets pulled along. Okay. So what I'm trying to show you here, this is what the blade sees, and this is from figure 3.7, and I believe this is figure 3.7 from the, I believe it's from Piggott. Let's just take a look back here at Jaw. Yeah. It's a little bit like figure 3.8 from Jaw, but if you dig into Piggott, I didn't bring Piggott with me. Do you have it? I don't have it yet. Yeah, there's a copy on the website. Nevertheless, this is common to all wind turbine technology. So this is where this is a little eyeball looking at the end of the blade. Mm-hmm. This is the wind coming in towards the blade. This is the velocity of rotation. So the blade is actually coming towards the wind. So this is the relative velocity of the wind. So and again, it's not that easy because we've already talked about the wind comes into the turbine this way, the thing's spinning this way. So however fast it's spinning down towards, that's the relative velocity. Yeah. So the drag force is whatever force is sort of pushing the blade back, keeping it from spinning. But the lift force is what's pulling it along. So as long as this lift force is in this direction, it's going to suck that turbine around in a circle. That's exactly how these things work. Kind of weird. That's how they work. It's flying through the air in a circle. Okay. Yeah. And of course, just like as in an aircraft, so here's the relative velocity of the wind coming in. This is the lift. This is the angle of attack. I just drew it in here as a little alpha. There's going to be some optimal lift, just like if you're flying along in your airplane, if your wings like this, you're going down. If your wings like this, yay, we're going up. It's a little more subtle than that because the wing has some shape to it.
Right.
But if you tip it up too much, whoopsies, stall. So there's a sweet spot. The whole point of this graph is just showing there's some kind of sweet spot. So this is figure 3.8 and 3.9. This must be out of the Piggott text. But there are also, if you look, this is also in chapter 3 of JAW. So the components of the circumferential force. The circumferential force is the force that's literally pulling the turbine blade around in a circle. Yeah. So this is just showing there's some optimal in there, some optimal angle.
Yeah, it's like you're good,
Yeah.
and then you're not good.
Yeah. And this was some other calculation we did for Jesse Melvin was building a Stirling engine a few years ago. There's the hot side, there's the cold side. The mass has some piston, the gas has some energy. There's a point where the high pressure is the low pressure, the volumes are equal. Let's see how far we got with that. I think that's where we left it, but this was sort of a start towards showing how much power there was in a Stirling engine. Okay, so we covered a lot today. We really did. If we go back here to the website, I'll just give you a quick little review of what we did. Started out with Stirling engines. I showed 3 videos: the alpha, the beta, the gamma. We tied the Stirling engine in with the ideal gas law. I showed that energy is or pressure is more or less specific energy, energy per unit volume. I talked a little bit about temperature, talked about the ideal gas law. We then derived the moment of inertia for a ring or a flywheel, and that has relevance both for the Stirling engine and for the wind turbine. We did a little bit of units conversion, a little bit of dimensional analysis. I showed you the pressure volume cycle for a Stirling engine. We started calculating the power. And to do so, you'd have to go all the way around this cycle and see how long it took to do that, etc. We went through a little spreadsheet exercise. Always kind of handy, get yourself a little spreadsheet so you don't have to redo the problem every single time. Let's save that guy here. Courses. 242. Rotational kinetic energy. Then finally, we kind of wrapped it up with rotor design. Talked about linear versus angular velocity, linear versus angular acceleration. Talked about tip speed ratio. Labeled that as lambda per jaw 336. Also mentioned the fact that forces are vector quantities. They're a sum of a drag force and a lift force. Whether you're talking about houses blowing over or wind turbines spinning, they're both critical to that calculation. and then looked at the wind turbine blade spinning to see a little bit about how that works. Also talked about the stall angle on a blade, and then played around a little bit more with Stirling engine power. Okay, that's all I got. I'm going to pause it there. I'm going to put I don't think I have it here yet on the website, but I'm going to put something up asking you to post your project. Well, it actually is here. And let's see what we got here. Let's see what we got here. Yeah. That's what Tim put up there. Yeah. So that's just kind of a little warm-up project. So do that.
Ricky went over that last week.
Perfect. Yeah. Yeah. And this is not the project. It's just
This is a warm-up tour of the project.
Exactly. Yeah. Okay.
Just to get your marbles rolling.
Marbles rolling around the head. Yep. There we go. Okay.